Okay, welcome back. Okay, so now we're going to do some examples of applying the theorem from the last video. So in all three of these examples, it involves going to be taking the derivative of an exponential function, but in different cases, we're going to be combining rules because, like for example, we're going to have a chain rule here in the exponent when we take the derivative of the exponent here. Here we're going to involve a quotient, right? And then of course here we're going to deal with an application for an exponential growth problem, okay? So remember when we talked a while ago in previous videos that exponential functions and logarithmic functions are very important and are used in many different applications. Exponential functions are used in growth and decay application functions, okay? Logarithmic functions are used at rescaling large numbers. For example, when we're dealing with the Richter scale on measuring the intensity of earthquakes, or we're looking at the decibel scale for the intensity of the sound, all those are on logarithmic scales to help us deal with either really large numbers or, large values, if you will. So anyway, let's move on and let's do some of these examples. So the first one, we want to find f prime of x. Okay, so it's an exponential, right? So it involves, all we're going to do is repeat. So if it's e to the u, so let's say this is u, right? So e to the u, and then we're going to multiply by the derivative of u. Or if you want to look at this as g of x, just like the theorem states, the derivative of this e to the g of x is equal to e to the g of x times the derivative of g of x. Okay, so remember, this is e to the g of x, right? So f prime of x is equal to e to the g of x times g prime of x. So let's do that. So now we're just going to repeat e to the tangent 2x times, now we're going to do the derivative of the exponent, which is tangent 2x, but tangent 2x involves a chain function too, because we have a function inside the tangent, so we're going to use the chain rule. So this will be, the derivative of this is actually going to be the derivative of the outside, which is secant squared. So we're going to have secant squared 2x, then times the derivative of the inside, which is 2. So our final derivative is going to be, I'm going to rearrange these, so it's going to be 2 secant squared 2x e to the tangent 2x. And that becomes our final result. Okay, so that's the derivative of f of x. Now, let's go on to the second one. So this involves a quotient, so we're going to end up doing the quotient rule here. There's no way to really simplify this. So, I mean, you could put it as x to the -1 and do product rule, but let's just do the quotient rule. Okay, so this is going to be what? Oops. Let's do it this way. Y prime is equal to, okay, so it's going to be high D low, so it's going to be e to the x squared times x minus, oh, no, I got that wrong. Got it backwards. Low D high, so it's going to be x times the derivative of high, so low D high. So the derivative of x squared is going to be e to the x squared times the derivative of the exponent, which is 2x, minus high D low, which is going to be e to the x squared times the derivative of the bottom, which is just 1, right? We just get 1 there. and divided by the bottom squared, which is just x squared. And so let's simplify this. We get 2x squared e to the x squared minus e to the x squared over x squared. Let me see. Let's factor out e to the x squared. So that's going to give us 2x squared minus 1 over x squared. And what does that give us? Is there anything we can do with that? I don't think so. Nope, that's it. So that is our derivative. Okay, now let's do an application problem. So in the third example it says, a colony of mosquitoes has an initial population of 1,000. So that's this here. So notice one of the things, before I go on, so the general form of these, if you remember from pre-calculus and other math classes, is this is A naught e to the kt, right? Where this is the initial population or the initial amount, okay, if you're talking about something else. So anyway, let's continue. It says, so after t days, the population is given by this function here, 1,000 e to the 0.3t exponent. Thus, the ratio of the rate of change of the population to the population is given by, it says, show that the ratio of the rate of change of the population a prime of t to the population a of t is constant. So we want to show that there's a constant rate of change. Okay? Now, the constant rate of change is going to be, I'm going to tell you, it's going to be this 0.3. Okay? So what they want us to do is show that the ratio of the rate of change of the population, a prime of t, to the population a of t is constant. Okay, so let's do that. So, what's a prime of t? A prime of t is equal to, well, this is just a constant multiple of this. So this is the function, so a of t, the derivative of t is going to be 1,000 times the derivative of this, which is just going to be e to the 0.3t, right? So we'll have 1,000 times e to the 0.3t. And then we're going to multiply by the derivative of this exponent here, which is just going to be 0.3. So 0.3 times 1,000 is 300. So we're going to get 300 e to the 0.3t. And now we're going to take the ratio of this to this. So now we're going to take a prime of t divided by a of t, which is then going to equal 300 e to the 0.3 t divided by 1,000 times e to the 0.3t. Well, this just reduces to 300 over 1,000 which gives you 0.3. These cancel. These divide out. And that's it. So we just showed that the ratio of the derivative to the original function is constant. So the ratio of the rate of change of the population to the population is the constant 0.3. So remember, a prime of t in this case, and again in the case of when you're talking about population growth or decay, it's a rate of change. It represents the rate of change of the population. Okay, and so that ratio of the rate of change of the population to the population is always constant. All right. Next, we'll talk about logarithmic functions. And so we're going to see something very similar to what we've been doing with exponentials that we're going to see with logarithmic functions as well. Okay? See you next time.